The ancient Greek philosopher Democritus theorized that all that existed were atoms and the void, and all material things were comprised of these tiny bits of matter called atoms. Today, the essential features of this theory continue on, and many people believe we're entirely comprised of nothing but subatomic particles, which are thought to be tiny bits of matter that are the fundamental building blocks of all things. But have you ever asked yourself, what is a particle? Are particles fundamental bits from which all things are built? Or has modern science revealed that the subatomic world is less material than we realize? A view held by many today is physicalism, which is sometimes equated with materialism. It essentially is the belief that everything that exists, every substance, is a physical substance, and every substance only has physical properties, and so every event must have a physical cause as well. On this view, all that we are reduces to physical objects or substances. In the past, and many laymen still today, believe that all things reduce to tiny bits of matter we call particles. However, this view has been challenged by modern scientific research, and with the rise of quantum field theory, a better understanding of matter is emerging. Physicist Dr. Nigel Cundy points out quantum field theory is the underlying fundamental theory that describes all of physical reality, and which everything else builds upon. It is a theory that combines quantum mechanics and special relativity, and can be seen as an extension of quantum mechanics that covers the analysis of systems with many particles and fields within a uniform theoretical framework. In other words, it is the theory that describes the operations and actions of the underlying subatomic world. However, in quantum field theory, particles are not perceived to be tiny balls or bits of matter like we traditionally think. That view of particles is an artifact of previous theories that are no longer viable. Instead, particles are better understood as excited states of quantum fields and are completely described mathematically as ripples within a quantum field, not little bits or balls of matter that are bouncing around in space. Cundy says, "The classical imagination, which underlies modern philosophy, has failed us. We still think of particles in modern physics, but we no longer mean the same thing by the word that people like Newton and Boyle did. Instead, he defines a particle as a metastable state, which carries a definite energy and momentum, and which corresponds to a particular set of creation and annihilation operators. A particle is thus an energy momentum excitation of the underlying matter field." Note that this definition is contrary to the classical definition of a particle, which implies an element of spatial location. Likewise, Walter Schmidt says, "Particles are actually waves in different types of fields. This goes for all the particles that we are made of. We are all just made of waves in a field. The vacuum is not something empty, a big nothingness, but contains fields that are waving all the time. What looks to us as a billiard ball on the billiard table is actually a bunch of waves moving from the cue to the pocket." In other words, there's nothing we know of a particle in quantum field theory that is not a mathematical description of a wave equation. The old view that a particle is a tiny, indivisible bit is not part of quantum field theory. Physicist Eliano Pessa notes within quantum field theory, defining exactly what particles are can be difficult, and various interpretations can follow. However, he points out the possibility of a particle interpretation of quantum theory has for the most part been ruled out, and a new understanding of particles must be implemented. The solution entails the idea that particles should be considered as merely the byproduct of interactions between quantum fields and an environment. They are emergent mathematical constructs of underlying fields. A particle is nothing but an effective field description of a complicated dynamics coupling the environment and its fields. The solution we have sketched above entails the disappearance of the hexiatus of particles, which are reduced to mere auxiliary constructs, useful for practical purposes, but in turn making reference to deeper constructs. For these philosophers, the problem now becomes, what are these constructs? Thus, particles are best understood as emergent mathematical constructs from underlying fields. Many modern physicalists who are aware of these issues try to bypass this and argue everything reduces to quantum fields, which would be the basis of all matter. But with this in mind, the next question is what is a quantum field? And this can be more difficult to define, and quantum fields do not appear to be underlying objects or fundamental material substances. And the more we try to understand the basis of all reality, the more abstract things become. Walter Schmidt says, a field is anything that can assume a value in every part of space-time, and he says that fields are that which give rise to particles. Fields seem to be more mathematical than concrete. David John Baker demonstrated that many of the problems particle interpretations have also apply to field interpretations. Wave-functional space is equivalent, in a mathematically rigorous sense, to the Fock space that represents states as particle configurations. This has the consequence that two of the most powerful arguments against particles are also arguments against such a field interpretation. And this in turn indicates that field interpretations are not, as many have assumed, a readily available alternative to particle interpretations. If the particle concept cannot be applied to quantum field theory, it seems that the field concept must also break down as well. Now, his paper is complicated, but in a nutshell, what he shows is that there are many mathematical problems in saying quantum fields are fundamental. Baker concludes, it seems that in many ways fields and particle interpretations must stand or fall together. Particles and fields essentially seem to be representations, so just appealing to fields to escape the problems that show particles cannot be fundamental doesn't work, because a lot of the same mathematical issues come up. Maynard Coleman notes that physics lacks a coherent account of fundamental issues, such as the definition of objects. Quantum field theory doesn't really tell us what substance quantum fields are. Instead, we only get an understanding of structures, relations, activities, and properties. He says, it sounds like having a marriage without spouses. And he also notes, a quantum field instead assigns abstract mathematical entities, which represent the type of measurements you could conduct, rather than the result you would obtain. Some mathematical constructs in the theory do represent physical values, but these cannot be assigned to points in space-time, only to smeared out regions. It is not at all clear what a particle or field even is. As Coleman notes, quantum field theory works without any relation to a fundamental substance that gives rise to fields and particles. Whatever matter is, it is not made of matter. Things get even stranger when we talk about the wave function of a particle. Quantum mechanics shows us in the absence of measurement on a particle, there is no discrete physical particle, but instead something called a wave function, which is just a mathematical probability of where the particle could end up. However, prior to measurement, there are no hidden variables that indicate the particle was already there and just waiting to be found. All that exists is the wave function, not a material particle. The key to understanding what is happening is that matter doesn't exist as a wave of energy prior to observation, but as a wave of mathematical potentialities prior to observation. Bruce Rosenblum and Fred Kuttner say it like this: the waviness in a region is the probability of finding the object in a particular place. We must be careful. The waviness is not the probability of the object being in a particular place. There is a crucial difference here. The object was not there before you found it there. In other words, prior to measurement, experimental results in the mathematical formalism of quantum mechanics imply there is no physical particle. Measurement causes the wave function to collapse to the physical particle, but nothing was physically there prior to measurement. Werner Heisenberg said, "The conception of objective reality of the elementary particles has thus evaporated, not into the cloud of some obscure new reality concept, but into the transparent clarity of a mathematics that represents no longer the behavior of particles, but rather our knowledge of this behavior." But if there is no scientific evidence that the underlying subatomic world is material, then what even is matter? In other words, if all we can induce is particles ultimately reduced to mathematics, then the evidence indicates that our material reality is a construct of underlying information. Science was once thought to point to physicalism or materialism, but instead, it has revealed the inadequacy of these beliefs. It is fitting that physics, the science that gave rise to materialism, should also signal the demise of materialism. During this century, the new physics has blown apart the central tenets of materialist doctrine in a sequence of stunning developments. First came the theory of relativity, which demolished Newton's assumptions about space and time. Then came the quantum theory, which totally transformed our image of matter. This is also supported by the holographic principle, which suggests the entire three-dimensional universe can be stored as two-dimensional information. The way it is explained is hypothetically, if something were to fall into a black hole, all the information of that object would be imprinted on its surface like a 2D image of what was once there. This was derived from the discovery that when something is added to a black hole, the volume doesn't change, but the black hole's surface area does change. In other words, the information of a three-dimensional object is encoded on the two-dimensional surface on the outside of the black hole. However, what is derived from this is the inference that all the information of the 3D universe could be like a hologram of this two-dimensional information, because the physics of black holes is similar to the physics of the singularity before the expansion of the universe. So the Big Bang and the expansion could be modeled in a way that is like a holographic projection of underlying information. In other words, this would mean all the matter of the universe is an informational construct, not built by tiny bits of matter. Leonard Susskind says, "The three-dimensional world of ordinary experience, the universe filled with galaxies, stars, planets, houses, boulders, and people, is a hologram, an image of reality coded on a distant two-dimensional surface." Thus supporting the notion the three-dimensional universe is an informational construct, not composed of fundamental material particles. What particles actually seem to be is constructs of mathematical information, which interestingly enough correlates to how we experience the physical world. It was Bishop Berkeley who argued that the physical world is nothing more than mental experiences or information, meaning anything perceived in the physical world is not a real substance, but a collection of mental properties. So think of what you experience. You experience properties. You experience mental things like colors, sounds, textures, forms and feelings, etc. What you experience are properties, not the objects directly. An idea that goes back to David Hume is something called bundle theory, which is the idea that physical objects just exist as a collection of properties, and if you remove the properties, there is nothing left to describe an object. So think of an apple. You can describe it as round, red, hard, and tasty. However, if you remove all the properties, what are you left with to describe this object? Susan Schneider says, "Pure property ontologies need to take physical objects as metaphysically derivative, even objects that physics regards as fundamental. Objects are instead bundled out of properties, or they are properties." To elaborate further, a color is a mental experience, which cannot be reduced to something physical. The scientific explanation of how we see color is that an electromagnetic wave hits the eye, creating a biochemical state, which then creates a neural pattern in the brain. But nothing in this transfer of mere information is the experience of color. color is purely a mental experience, not a property that exists without a mind. If you touch water, you experience wetness. But wetness is only a mental sensation. Wetness only occurs when a mind experiences water. The same applies to taste sensations. Sugar doesn't taste sweet unless there is a mind there to experience it. Thomas Nagel says, if a mental event really is a physical event in the sense and nothing else, then the physical event by itself, once its physical properties are understood, should likewise be sufficient for the taste of sugar, the feeling of pain, or whatever it is supposed to be identical with. But it doesn't seem to be. It seems conceivable. For any physical event, there should be a physical event without any experience at all. Experience of taste seems to be something extra, contingently related to the brain state, something produced rather than constituted by the brain state. So it cannot be identical to the brain state in the same way that water is identical to H2O. Todd Burris and Trent Doherty present a similar argument, called the problem of positive properties. When we say an object is physical, there is no way in which we describe it where we refer to it as an object without reference to our mental experiences or properties. We always describe physical objects in ways that are mind-dependent. So we lack positive properties that indicate the object is a distinct physical substance. A physicalist needs to show there is something there beyond the mental experience. What intrinsic qualities do physical objects have that are intrinsic to the objects themselves? Physicalists need to show there is something to the alleged mind-independent objects beyond their extrinsic, relational, or purely formal properties. As they put it, perhaps none of the familiar properties of corporeal substances characterize bodies as they are in themselves. Perhaps all their properties are merely formal, extrinsic, relational features. It could be that there is nothing that a physical object is like in itself. Perhaps there is nothing more to such things than the relational features they bear to other things, particularly perceiving minds. Once the possibility is raised, it can take on a default position in that one realizes, in raising the possibility, that we are nearly devoid of reasons to think allegedly extramental entities have positive properties. All of what we experience is a world of mental properties. So why posit physical substances beyond our mental experiences if such substances are not necessary? We experience a mental world, not a physical one, and we do not need to posit anything beyond the mental properties to understand the world around us. In other words, all things physical appear to be mental properties or information. Keith Ward puts it like this: any physicist will say that brains are mostly empty space, in which molecules and other strange particles buzz about in complicated ways. It seems as though physical objects, when not being observed, have no colors and no sounds, smells or tastes either. Sounds like colors are not physical events. Neither are smells, tastes, or sensations. Things do not smell like, taste like, or feel like anything when nobody is smelling, tasting, or feeling them. The physical world, it seems, is totally vacuous. No colors, sounds, smells, tastes, or sensations. What on earth is left? Susan Schneider applies this same logic to the subatomic world. As we noted earlier, in quantum field theory, particles are completely described by mathematics, without any reference to an entity. However, if the only way we can differentiate an electron from a proton within physics is mathematically, then why isn't the mathematical equation part of the makeup of the electron and the proton, the same way redness is a property of an apple? Much like the idea of bundle theory about physical objects, if you strip away the mathematical description of a particle, you're left with nothing to describe it. So why should we posit real physical entities when philosophically there is nothing there but the mathematical information, which, just like the physical properties, can be explained purely as mental information? As Schneider says, physics is highly abstract, and the physicalist lacks physically kosher truth makers for its claims. Physics is not physicalistic, if you will. In short, fundamental physics is mathematized physics. As Timothy Williamson has remarked, What, for a start, is the natural world? If we say it is a world of matter, or the world of atoms, we are left behind by modern physics, which characterizes the world in far more abstract terms. Meinrad Kuhlmann says, what we call an electron is in fact a bundle of various properties or tropes, 3 fixed essential properties, mass, charge, and spin, as well as numerous changing, non-essential properties, position and velocity. A particle is what you get when those properties bundle themselves together in a certain way. Thus, all of matter can adequately be explained as mental information. Now we must ask, if material particles are not the fundamental basis of reality, then what is? The solution is pretty obvious at this point. If matter can be reduced to mathematical abstractions and mental information, then the basis of the physical is consciousness. Instead of matter creating mind, the evidence implies the opposite. Mind creates the appearance of matter. Such an idea has already been proposed by cognitive scientist Donald Hoffman. Instead of matter being the basis of all consciousness, consciousness is the basis of what we experience as matter.
Green also concludes that, he says in his recent book, The Fabric of the Cosmos, that space, like electrons, comes in discrete, indivisible chunks. Space and time are pixelized. We need that to get our ultimate theory of space and time. And the very fabric of space and time is composed of more fundamental spaceless and timeless entities. But he doesn't know what they are. I have a proposal. Those spaceless and timeless entities that they're looking for are in fact conscious agents.
So what we see in modern science points away from physicalism and is better explained by an idealist perspective. Mind is fundamental and matter is emergent. Thus, modern science was once thought to point to physicalism. The universe was cold and dead. Meaning and purpose were mere subjective constructs. Humans were biological robots, merely the product of atoms. But beneath the atoms, the world revealed itself to be more abstract, mental in nature. The fundamental particles, once thought to be the basis of reality, were revealed to be constructs of a mental reality. The old Cartesian notion of humans being ghosts and machines might be dead, but not because there are no ghosts, but because there are no machines.
The future, at least of this development, will be that we start actually with information. So information is going to be our starting point. And space-time is not something that we start with. We forget about what space is and what time. And then somehow the information, by thinking about how much information is, what information is doing, then the space-time will, what we call, be emergent. It will come out of just a bunch of zeros and ones.
So the idea is that the concept of space, of distance, all the spatial concepts we deal with in science are emerging from that deeper level. They're not fundamental in the world. They're derivative.
In the hunt to rectify quantum mechanics with relativity, physicists discovered something known as the holographic principle, a theory which suggests the entire three-dimensional universe can be seen as two-dimensional information. In other words, the whole three-dimensional universe, the particles that make up reality, would emerge from underlying information in quantum field theory.
People finally began to articulate this new principle, this holographic principle. And what it said is that all the things that were falling inside a black hole were somehow captured in a preserved image at the horizon itself.
So if the information is not lost on the surface, the information is not lost inside because they are equivalent.
All the information about those objects, what they were like in their three-dimensional existence, was preserved or encoded on the surface of the black hole. And that's a little bit like a hologram.
Well, that suggests that maybe that idea may apply more broadly to the universe as a whole. Maybe the three-dimensional objects, us, everything in the world around us, maybe all of the information in these objects is carried, is smeared around a distant two-dimensional surface that surrounds us, and we're just in some sense a holographic projection of that distant data.
The holographic principle tells us something quite astonishing. It says that our ideas of volume, of the real world in a sense, might be a kind of illusion.
The holographic principle only worked in theory at first, with no observable data to back it. But all that changed in 2017, when a peer-reviewed study published observable evidence for the holographic principle. They tested the model against cosmological observations of the early universe and found that the holographic model is compatible with the data that is found in the cosmic microwave background radiation. From looking at irregularities in the background radiation, their team found that simple equations of quantum field theory could explain almost all the cosmological observations, is marginally a better fit than the standard model, and could potentially explain apparent anomalies. But this would mean evidence in the cosmic microwave background radiation infers three-dimensional reality is an emergent informational construct. Observable evidence infers reality as we experience is not fundamental but emerges from the quantum realm. This piece of data only correlates to a study from later that same year, which points out entanglement is an inevitable feature of reality. Entanglement happens when two particles interact in a way that their quantum state or wave function cannot be described independently or without the other. However, if you were to separate them by a great distance, a change to one instantly affects the other. This has been demonstrated in several experiments, and now a new study shows that such a phenomena is an inevitable feature of reality. We show that any theory with a classical limit must contain entangled states, thus establishing entanglement as an inevitable feature of any theory superseding classical theory. In other words, any theory which purports to describe reality must include quantum entanglement as an underlying fundamental feature of reality. If you entangle two particles and separate them by a great distance, a change to one will instantly affect the other, regardless of the space between them. So the information between them doesn't seem to be affected by space, implying space is not fundamental for the underlying world of quantum mechanics, but an emergent phenomena of the classical world that only exists after measurement.
Whereas space is just obviously not fundamental. Space is something where when you go from classical mechanics to quantum mechanics, space more or less disappears. In classical mechanics, what do you have? Some particles moving through space with some velocities. In quantum mechanics, you have a wave function of all those particles. And that wave function, we tend to talk a language that the wave function is a function of all the particles and their locations in space, but we don't have to talk that language. We can use what is called the momentum space description. We can completely describe the particles by how fast they're moving instead of where they are in the universe. And for that matter, we don't need to use any description at all. We can just use these quantum mechanical states in their own right, with no reference to space whatsoever.
Remember that in quantum mechanics, prior to measurement, particles have no defined properties or locations. In the absence of measurement, particles simply exist as a wave function of possible states they could take, and that includes the location of the particles. If particles have no defined locations prior to measurement, that would mean the information between entangled particles exists other than spatially. Spatial location only emerges after measurement. Thus, entanglement shows space is not fundamental, but emergent from quantum processes, correlating with the evidence from the holographic principle. The wave function of entangled particles is far more fundamental than the space between them. Therefore, the underlying information is more fundamental, and space is emergent. Space is just the illusion that particles are separated, not a fundamental feature of reality. Physicist Sean Carroll writes on his blog, Space Emerging from Quantum Mechanics, that the most likely way to explain the nature of gravity is to note space emerges from quantum mechanics, not that space is a fundamental property of the subatomic world. Physicist Haiyan Seok Yang says emergent spacetime is the new fundamental paradigm for quantum gravity. This new paradigm suggests space is not fundamentally real, but emergent from the underlying quantum realm. But it is not just space that is emergent from quantum entanglement. Einstein demonstrated space and time are one, so that would have to mean that time is also emergent from the underlying quantum realm, and an experiment from 2013 reveals this. The Wheeler-DeWitt equation, which calculated the wave function of the universe, noted the time factor dropped out, meaning time is also not a fundamental aspect of the underlying quantum world, but emergent in the classical world that we experience day to day. And in 2013, an experiment seemed to confirm this idea that time, along with space, is an emergent phenomena.
So in quantum gravity, now probably what's going on is what we're seeing is that the whole notion of space and time it's probably not really fundamental. So space...
That sounds incredible. That space and time is not fundamental. Space and time seem, in an ordinary sense, to be the most fundamental thing, and everything else seems to happen in space and time as sort of the fixed background.
Right. But what could be happening is that there are two different notions of time, a more fundamental one and an emergent one. So it's the emergent one that is part of the space-time, but there is a more fundamental one that makes sense without space.
Now, neither one of those new ways are obvious to us in our common perception, obviously, but Einstein put space and time together, which was a radical change. What you're saying is that the time that he might have unified with space may be an emergent time,
That's
and there's
right.
something more
There's a
fundamental
more
in
fundamental
time.
one.
Thus, all of what we experience, space, time, matter, all seem to be emergent constructs of the classical world, not fundamental aspects of reality. Experimental data shows us matter and spacetime are emergent, while in contrast, another experiment shows the wave function is fundamental to reality. At the advent of quantum mechanics, many suggested the wave function was not actually a part of nature, but just a mathematical tool which represents our lack of knowledge about the system. Yet a recent experiment gave strong evidence the wave function should directly correspond to reality. So the wave function, a mathematical probability of possible states in Hilbert space, does correspond to the fundamental nature of reality. Space-time is nothing more than a construct emerging from the wave function in Hilbert space.
Space-time is not fundamental. That space-time is, if you like, an effective emergent description from something else.
The implications of this are quite astonishing, because the wave function is not a physical object extended through space, but a mathematical probability of where physical particles will appear in space. Sean Carroll explains, mathematically, wave functions are elements of a mathematical structure called Hilbert space. That means they are vectors. We can add quantum states together, the origin of superpositions in quantum mechanics, and calculate the angle or dot product between them. The word space in Hilbert space doesn't mean the good old three-dimensional space we walk through every day, or even the four-dimensional space-time of relativity. It's just math speak for a collection of things, in this case, possible quantum states of the universe. The underlying truth of the universe is a mathematical reality from which the classical world we experience emerges. What we think is objectively real is nothing more than an emergent construct of underlying mathematical informational processes. To further confirm this, Brian Whitworth looked at specific features of our universe and compared them to a virtual world. What he found was 11 key features of the universe are better explained with the idea of a virtual reality instead of an objective reality with fundamental space-time and matter. Features of our universe, like the maximum speed, the Big Bang, quantum transitions, and wave function collapse, all make more sense in a virtual world. In other words, the philosophical conclusion is our universe behaves more like a virtual world instead of an objective reality. This aligns with the scientific data we just discussed, which shows space-time and matter are emergent. On top of this, the work in theoretical physics is leading us towards the conclusion the rules of physics and gravity are emergent from the underlying spaceless, timeless quantum realm. All the evidence infers that physical reality is not fundamental, but emergent from underlying information. But there is a much deeper implication here. The wave function explains the emergence of spacetime, but the same underlying mathematics has been seen to parallel conscious thought processes. Quantum superpositions do have a vague similarity to how we think and mentally operate. For example, we often hold conflicting positions simultaneously before making a final decision, like how the wave function is in a superposition of multiple states before final collapse to one definite outcome. We can bounce around between different ideas in our head, similarly to quantum tunneling. This similarity might be more interesting than we realize. In 2009, physicist Diederik Ertz took this one step further and published a paper noting that our cognitive processes can be readily modeled using the mathematical formalism of quantum mechanics. In other words, our inner mental world of thoughts, qualia, and emotions can be modeled in terms of Hilbert space and quantum processes, the same processes that give rise to space-time and matter. Many suggest this is just a coincidence, But there have been hints that it goes beyond this. Within the past few years, a number of papers have been published supporting quantum mind theory. Information processing has been reported to exist inside microtubules, and another study has shown that tubulin protein molecules self-assemble via quantum tunneling. We even have evidence to suggest that quantum vibrations are coming from microtubules. Quantum biology researcher Anirban Bandyopadhyay said the microtubule appears to be a fundamental information processing device in biology. More and more evidence keeps coming out supporting that there are quantum processes in the brain, cohering with the field of quantum cognition that the inner world of the mind should be modeled with the properties of quantum mechanics. This all suggests quantum cognition is not just a way to model cognitive processes, but directly applies to the very nature of the mind and the brain. Stuart Hameroff also points out that since the inner mental world of the mind can be modeled like the quantum world, the brain is more likely to be quantum computing instead of classically computing.
Okay, so quantum cognition is this mathematical approach, and from Wikipedia they say, well, the field clearly distinguishes itself from the quantum mind as it is not reliant on the hypothesis that there is something quantum mechanical about the brain. So they're trying to have their cake and eat it too. They're trying to say we're using quantum mathematics, but we don't want to go on that risky limb that there's quantum biology in the brain, because everybody knows the brain's too warm, wet, and noisy to have quantum computing going on. Nonetheless, some of us do feel that the brain has quantum biology, and it has to. And for example, if a classical system would try to simulate a quantum system, you'd have exponential slowdown, as Feynman showed. It would be, you wouldn't be able to do it. It would involve so much computation. And what would be the point of using a classical system in the brain to simulate a quantum system if you could have the quantum system?
Quantum cognition seems to fit with recent experimental data of quantum mind theory and recognizes the basic idea that our thoughts and emotions behave like quantum superpositions, not like physical objects or chemicals bouncing around inside our heads. Thus, the inner world of the mind, our thoughts, emotions, dreams, qualia, etc., would be distinct from the physical world, like how Hilbert space is distinct from space-time. In other words, there is a parallel distinction with the spaceless, non-physical reality of Hilbert space, from which space-time emerges, to how the spaceless, non-physical reality of our minds, our thoughts, emotions, dreams, is distinct from the external physical world. This is a common understanding with regards to the mind-matter distinction in philosophy of mind. No one can demonstrate how a mental phenomena would emerge from a physical substance. A feeling of pain can never be equated to an electrical signal. The mental experience of color cannot be equated to electromagnetic waves which hit receptors in our eyes. There is merely a correlation between the two, but one cannot explain how qualia could ever possibly emerge from this. As John Searle says, how does a mental reality, a world of consciousness, intentionality, and other mental phenomena fit into a world consisting entirely of physical particles and fields of force? Colin McGinn says, the problem with materialism is that it tries to construct the mind out of properties that refuse to add up to mentality. Thomas Nagel says, if a mental event really is a physical event, in the sense and nothing else, then the physical event by itself, once its properties are understood, should likewise be sufficient for the taste of sugar, the feeling of pain, or whatever it is supposed to be identical with. But it doesn't seem to be. It seems conceivable for any physical event there should be a physical event without any experience at all. Experience of taste seems to be something extra, contingently related to the brain state, something produced rather than constituted by the brain state. So it cannot be identical to the brain state in the way that water is identical to H2O. In other words, no amount of introspection can ever be reduced to the chemistry of the brain.
There's nothing about introspection that leads you to sense that your subjectivity is at all dependent or even related to voltage changes and chemical interactions going on inside your head. Okay, you can feel, you can drop acid, you can meditate for a year, you can do whatever you want to perturb your nervous system. You can feel yourself to be one with the universe, and at no point in that transformation do you get a glimpse that there's 100 trillion neurons in your head, or synapses in your head that are doing anything.
But what if we have it backwards? What if the problem is we think that mind arises from the brain, when in reality, what if the experience of the physical world arises from the mental world, correlating to how space-time emerges from Hilbert space. The correlates can no longer be ignored. The scientific evidence points to the fact that space-time and matter are emergent from the wave function in Hilbert space, and the inner world of consciousness and mind can be modeled as Hilbert space in the study of quantum cognition. Add on the evidence for quantum mind theory, and the most parsimonious explanation is space-time emerges from a shared inner mental world governed by a universal mind. The physical universe we experience is emergent from a necessary mind. This simply correlates to the idealist views of philosophy of mind. It is not matter that is fundamental and mind emergent, but mind is fundamental, and the experience of the physical world is what emerges from mind. Think of what we experience. It is a world of qualia. All we see can be described as mental without reference to any separate physical substance. It is completely impossible to describe the inner mental world in terms of physical interactions, but we can easily explain the physical world we experience in terms of qualia, shapes, forms, feelings, tastes, smells, etc. All of these are mental in nature, and the physical world itself can be reduced entirely to mathematics in how we describe it. Keith Ward says it like this: any physicist will say that brains are mostly empty space, in which molecules, atoms, electrons, quarks, and other strange particles buzz about in complicated ways. It seems as though physical objects, when not being observed, have no colors and no sounds, smells, or taste either. Sounds, like colors, are not physical events. Neither are smells, tastes, or sensations. Things do not smell like, taste like, or feel like anything when nobody is smelling, tasting, or feeling them. The physical world, it seems, is totally vacuous. No colors, sounds, smells, tastes, or sensations. What on earth is left? This correlates to what a few scientists have recently published, where they point out that there are interesting similarities between neural networks and the cosmic web of galaxies. Recently, astrophysicist Franco Vazza and neurosurgeon Alberto Faletti wrote an article on the similarities between both. Is the apparent similarity just a human tendency to perceive meaningful patterns in random data? Remarkably enough, the answer seems to be no. Statistical analysis shows these systems do indeed present quantitative similarities. They note the similarities line up with information processing, power spectrum analysis, total neuron to total observable galaxies, and in many other ways. If idealism is true, then this is readily explainable and fits with the rest of the data we have presented. Both form the same physical structure because both are emergent from an underlying mental reality. Under idealism, the brain is simply seen as the physical manifestation or second-person experience of a first-person conscious experience. And it fits with the idealist view that the whole universe would be structured in the same way, since it is also the emergent physical manifestation of mind. Thus, given the philosophy combined with the direct scientific evidence, the conclusion is undeniable. As Max Planck said, all matter originates and exists only by virtue of a force. We must assume behind this force is the existence of a conscious and intelligent mind. This conclusion has already been reached by cognitive scientist Donald Hoffman. His model argues that given all the data we just discussed, the best explanation is space-time is emergent from consciousness.
The top was the conscious agent dynamics, long-term behavior, and then if you write down the wave equation for the free particle in quantum mechanics, it's exactly the same equation. This is the non-relativistic case. You can actually read off a one-to-one mapping between non-relativistic quantum mechanics and this agent dynamics. And I won't go through it. This is the actual read-off of the equivalence between space and time and aspects of consciousness. Now, that's non-relativistic, and I'll close by the relativistic. I mean, the ultimate thing is we want to have a relativistic quantum theory falling out of a theory of consciousness. And the direction I'm going on that, and I'm starting to collaborate with Chris Fields and some others on this, is to actually take a system of two conscious agents, and it turns out it can be represented by something called a geometric algebra that I've written down there. And that geometric algebra is precisely the geometric algebra that describes the relativistic quantum free particle, massless particle. So the idea is that we can get space-time coming out of this, Dirac spinors, And ultimately, using Penrose twisters, maybe even quantum gravity. So the idea is that this program, for it to be successful, has to start with consciousness and give us all of quantum physics, and then we've solved the mind-body problem going the other way.
The paradigm is shifting, and a new consensus is emerging. The old notions of the physical world being fundamental must be abandoned in light of the new scientific data. Consciousness is fundamental, and the experience of the physical world is what is emergent. The data has been building up in several fields, from philosophy, quantum physics, neuroscience, biology and chemistry, and cosmology and holography. A new paradigm in physics is emerging, one that turns the old materialist notions on its head. We are not the accidental products of the blind workings of matter. The workings of matter are the products of the mind. The evidence leads to the conclusion our universe is an emergent world from an underlying consciousness. The paradigm is shifted, and the way we view ourselves and the universe will never be the same.